The recording had started. So, can anyone please confirm once again? Is my screen visible?
Yes, sir.
And am I audible as well?
Yes, sir.
Okay, thank you. So, good evening, everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow in Department of Mathematics, IIT Patna. I am your NPTEL-PMRF Teaching Assistant for the course Probability and Statistics. This course is offered by Professor Somesh Kumar. He is faculty in IIT Kharagpur. This is a 12-week course actually, and this is the second week live session for the course. So I hope if you people have any doubt, you may directly ask me here, or you can ask via comment or discuss forum as well. Okay. So in previous week, like in first week, we have discussed about sets of algebra of set. Okay, in which we have discussed about ring, field, sigma field, semi-ring, and probability space, sample space, etc. We have also discussed about some definitions of probability, actually three definitions of probability. Okay, we will start from there today. Okay, like introduction to probability or probability. So before starting the definition of probability again, let me just taking some snapshot of some other terms we are frequently used in probability. Okay? So introduction to probability. So we frequently use the term like experiments. Okay. So experiments are conducting something in certain condition. Okay, which results in some outcomes are called experiments. These are of mainly two types, as we have already discussed. The one is deterministic experiment, and the second one is random experiment. Okay, so in deterministic experiment, when we perform the experiment, we usually know what we will get as an outcome or result. Okay, suppose when we mix H2 and O2, that is hydrogen and oxygen, in a fixed amount or fixed proportion, then we will get H2O, that is water. Okay, so we already know that when we like uh, react hydrogen and oxygen in a fixed proportion, the outcome will be water. But in some other cases where the outcome may vary, we have a set of outcomes, but we will not sure that which outcome will come. Okay, that which result we will get at a particular trial. So those kind of experiments are known as random experiments, like tossing a coin. Okay, when we toss a coin, we will know either we get a head or a tail. But at every trial, we will not sure that what we will get. It may possible that for 10 successive tosses, we will get head or tail, although it has a very less probability, 0.001 something, but still there's chance. Okay. So we will not sure at what trial what will be get. In a similar manner, like rolling a die, okay, selecting a card from a deck of card. These are the random experiments. Okay, so we have these kind of experiments in this in this course, which we will discuss. Okay, uh, some more things are like outcomes is there. What are outcomes? So when we perform random experiments, we will expect some results. Okay. Those results are called outcomes. Okay. So like again, when we roll a die, the outcomes will be either 1 or 2 or 3 or 4 or 5 or 6. These are the only 6 possible outcomes we will get when we roll a die. Again, suppose we will
Sir,
toss.
excuse me.
Yes,
Hello, sir. Good evening. I'm sorry to
good
disturb
evening.
you in between. I do have one office meeting and I'm not able to attend today. But I wanted to check quickly that the exam, whatever will be conducted for us, it will be a multiple choice one or is it a written exam?
Okay. So when this exam only, na?
Yeah,
This
probability
course
and
exam.
statistics.
Okay.
So April
So
26th is the exam date. I have registered
okay.
for the same. I wanted to know if it is a multiple choice or is it a handwritten exam.
Okay. I'm not 100% sure, but I think it's a written subjective exam will be there.
Okay, okay.
Okay. You need to
Sir,
submit. Yeah, sorry. Yes.
no problem, sir. Please go ahead.
Okay. You need to submit the assignments actually.
Okay,
Top 8 assignments will weight 25% of your mark, and the rest 75% will be on 26 when you will obtain the subjective exam.
okay, okay. It will be handwritten, you are saying.
Yes.
Sir, one more question is if so we have this weekly class which you are scheduling. It was supposed to be on Tuesday, but it is on Friday
Yes.
now.
Yes.
So will it be
Yes.
on Friday every week or it will be on
No, no,
Tuesday?
no, no. It will be on Tuesday every week. Due to some reasons, I postponed this class actually. Okay.
Okay, no problem,
Every
sir.
Tuesday at 6 to 8 p.m.
Okay, okay. Thank you, sir. Thank you so much.
Okay. Thank you.
And sorry, one
Yes.
last question. We have some 9 book recommendations in the portal regarding this particular subject, and I see that most of them are not available in handy, even online. We have to purchase them, and they look
Okay.
little
Okay.
expensive as well. Can you suggest like what exactly are the textbooks which we can go ahead and start reading with?
Okay. Okay.
Um,
I will try to give some PDF in this. Okay.
okay,
On my YouTube channel actually. Okay. From there, you can get the link in the description of this recording lecture. Okay. Or
okay,
you can go to my Google site. There you will get everything. Okay. I
okay,
will try to put 2 or 3 PDF books for this course. Okay. From
okay,
there you can follow. Okay.
okay. Thank you so much, sir. Thank you.
Okay. This one is actually my site, and you can connect me via LinkedIn as well. From there, you can access all these things. Okay.
Okay, sir, great. Yours is same name as mentioned in the portal now, right? In
Yes.
LinkedIn.
Yes.
Okay, thank
Yes.
you.
Yes. Okay, so we will discuss about outcomes. Okay, when we perform a random experiment, we will expect some results. Those results are termed as outcomes. Like when we roll a die, we will get either 1 or 2 or 3 or 4 or 5 or 6. Okay, there is all these 6 possible outcomes. Okay, when we toss a coin simultaneously. Okay, when we toss a coin simultaneously, a coin is tossed. Coin is tossed twice, or coin are tossed simultaneously. They both possess the same sample space. Okay, let me write it omega 1, and then omega 2 is like the first one carries head tail, tail head, and tail tail. Okay, these are the only 4 possible outcomes when we perform the above experiment. Okay, so these are called outcomes, and on the basis of these outcomes, we will define events. Okay, so events are nothing but subset of sample space, as we have already discussed, like event A or A1 is like two heads, A2 like two heads, that means only one possible out. Two, that is one head and one tail. So this implies head or tail or head. And similarly, we can define multiple events on the basis of a single random experiment. Again, we have different kinds of events as well, like mutually exclusive events. Mutually exclusive events, or these are also termed as disjoint events, because when two events are said to be mutually exclusive if there is nothing common in between. Okay, so if they have the intersection between those events are null or phi, then we can say that those events are mutually exclusive. Actually, mutually exclusive, suppose we have A1, A2 up to AN for lots of events, then if A1 intersection A2 intersection AN, these are disjoint events. Okay, and these are pairwise disjoint. When we have two events, then those are called pairwise disjoint. Otherwise, in general term, we say those are disjoint events. Okay, then exhaustive events are there. Exhaustive events are like the collection of those events whose union equals sample space. Suppose we have A1, A2, AN in such a way that A1 union A2 union AN, it comes out to be the sample space. Then, and also there is one more condition actually, A1 AI intersection AJ equals phi. Okay, if these conditions are satisfied, these two conditions, then we say that the AIs are exhaustive events. Okay, then again, we have independent events. Independent events. Independent events are like those events uh, which follow this rule. Like if probability of A intersection B equals probability of sorry, intersection into probability of B. If two events are in such a manner, then that the probability of their intersection is equal to the product of their probabilities, then those two events are said to be independent events. Okay. There is also equally likely events is there. Equally likely events are there. So those events, okay, suppose we have A1, we have A2, we have A3. So those events in which the probability of occurring the event A equals probability of occurring of event B, which is again equal probability of occurrence of event C, third event, that means then those events are said to be equally likely events. Okay. Like when we toss a coin or when we roll a die, when we say we toss a coin or roll a die, we will already mean that those coin or die are unbiased in nature. Okay. Then we have exhaustive events. Okay. Everything is okay up to this point. So we have three more definitions that we have already discussed. Like the first one is the classical definition or the mathematical definition of probability, in which the probability of an event E is defined as the number of elements or the number of favorable elements and total number of elements. These are nothing but the ratio of the favorable event to the total event. So this is classical definition of probability. then we will find some we will find some drawback of the classical definition of probability. Then we will define statistical or empirical definition of probability, in which we do nothing, just take the limit n tends to infinity m upon m. Here again, m is the number of elements in the favorable set, okay, and the total number of sets. And then again, we have the third definition, which is axiomatic definition of probability. This is the latest one. So in this definition, we define three axioms actually, okay, and those three axioms are like suppose we have a sample space S. S is a sample space and A be any event. Okay. Then the probability of the event A is defined in a way that we have already defined in the above, but it must follow three axioms actually. The first axiom is like the probability of an element of an event always lie within 0 to 1, the first event. This is called non-negativity. The second one is like probability of a sample space comes out to be 1. Okay. And the third one have a condition as well. Suppose if AI's I from 1 to is countable sequence of mutually exclusive and AI's intersection AJ equal 5. Then if condition that means these are mutually exclusive events, then the probability of union of AI is equal to summation of their individual probability. Okay. So if these three conditions satisfy, then it is defined as like axiomatic definition of probability. These we have already discussed. Now the again
Sir, may I
in
ask
this,
you-
yes.
Sir, where is the statistical definition of probability used?
Where?
The statistical P equal to limit n tends to infinity m upon n.
Okay. Okay. For that, just remember, try to remember like what is the drawback of the classical definition of probability. The drawback is, although there is more drawback, like the first one is equally likely probability. There will be equally likely events. So that is already a circular definition of probability. But the second one is if the denominator in classical definition of probability, if the denominator comes out to be infinity, then the overall probability will tends to 0. Okay. But in statistical or empirical definition of probability, we will use the concept of limit. And with the help of limit concept, we can solve this. Na? Because n may be infinity. It may, n tends to infinity. That means it may follow infinity. Okay. It may converge to
Okay.
infinity. Okay.
Okay.
Is it okay?
And sir, yes, sir. And the
Yes.
third point of axiomatic definition of probability, can you please explain again?
Yes, actually, axiomatic definition of probability means actually the definition is the same, but it must follow three axioms. Okay, that means if this p function is the probability function. Okay, so if it is a probability, then it must follow three definitions. Okay, sorry, three axioms, and these are the three axioms. And these three probabilities defined in the above two similar way. Okay, like a classical or the statistical way. Okay, the probability term is defined in the similar way, but it may follow, sorry, it must follow three axioms. That's why it's called axiomatic definition of probability. Okay, like the probability of is again same. Suppose you take a coin, okay, and you will start tossing up to 10,000, 50,000, 20,000 times. Okay, so you will repeat again and again, but at all the time, suppose if I am telling the event A is getting head. Okay, so usually we will know that the probability of head is nothing but approximately 1 by 2. Okay, so in every trial, if you will perform the tossing coin, you will always get the probability of head in between 0 to 1. Okay, it will not exceed beyond the before the 0, that means in negative or more than 1. So this first axioms will satisfy in each and every cases. The second one is again, suppose you toss a coin and each and every time you will get head only. Then at that condition, the probability of the event A, that is probability of getting head, is nothing but 1. Okay, so the probability of sample space equals 1. And the third one is this one. If the events are mutually exclusive in nature, then the union of the probability, the probability of their union is equal to the summation of their individual probability. These three are always hold. Okay, always held actually. So that's why these are called axiomatic definition. There is nothing extra definition of probability. These are three axioms that must follow by this P function, which we call probability function.
Thank you, sir.
Okay, so these are the axiomatic definition. Now we will discuss about conditional probability. We will discuss about conditional probability. So conditional probability, like we impose some more condition on sample space. Okay, so suppose first we roll a die. Okay, suppose first we roll a die, and then we will get either 1 or 2 or 3 or 4 or 5 or 6. Then suppose we impose some more condition that we again roll the die if we get an even prime number, a prime number which is even. So our condition impose on the even prime number, which is actually here. There is only one even prime number actually, which is true. So now we modify our sample space on the basis of the condition. So now our modified sample space will be 1, 3, 4, 5, 6. Okay. So we impose some condition on the sample space. And the definition of the conditional probability is defined as like the probability of the event A. When we impose the condition B, that means probability of A given B, we will read this as probability of event A given B equals probability of A intersection B divided by probability of B. Okay. You can also write it like probability of A intersection B is what? Number of elements in A intersection B divided by total number of elements in the sample space, suppose S, whole divided by probability of B, number of elements in B divided by number of element in sample space. Again, these S cancel out. So probability of A given B, which we can define is probability of A intersection B divided by probability of B, which can also be calculated as probability of, number of A intersection B, number of elements in the set A intersection B divided by number of elements in B. Okay, here you can observe. Now we actually modify our sample space on the basis of the condition. Here, what we have conditioned, given B. The condition is given B. And now, what is the definition? Modified definition. Number of element in the set A intersection B, but it is divided by the number of element in the B. That is the condition we have modified. So this is the conditional definition, conditional probability. Okay. We will solve some numericals actually on all those topics. Then there is one multiplication rule is also there. Multiplication rule of probability. Okay, so this is nothing but from here only, you can find the probability of A intersection B is defined as the probability of A given B into probability of B. This is a multiplication rule, or we can also define as the probability of B given A into probability of A. So this is the multiplication rule. That means the intersection probability is equal to the product of the conditional and the elementary probability. Okay, so these all are actually used. We will mainly going to solve Bayes theorem. I think everyone have already heard about the name Bayes theorem, which is also known as like posterior probability actually. Okay, so posterior probability, like we already have some prior information, and on those basis, we calculate the probability. So those probabilities are based on some already known probability. So that's why it is called posterior. Okay, so this is Bayes theorem, and in Bayes theorem, suppose let me write suppose E1, E2 are pairwise disjoint and exhaustive events. So these events are like pairwise disjoints. These events are pairwise disjoints, and these are exhaustive events. Okay, so these two conditions are satisfied. Suppose E1, E2 dot dot. These are the pairwise disjoint events as well as exhaustive events. So and then in that condition, the Bayes theorem or the Bayes probability is defined as the probability of EI given A. Actually, A is also, we need to define A as well. Okay, and A is our likelihood event actually. So likelihood event, that means this event A is actually related to all those EI's events. Okay, so these are, so this is termed as likelihood event. Okay, so the probability that EI given A is defined as probability of A given EI into probability of EI and divided by probability of A given EI into probability of EI, but this will be taken on the summation I from 1 to infinity. Okay, so this is the actually ratio only. Okay, and if you see, you will find out the probability of A given B, that is the conditional probability. The probability of A given B is what? Probability of A intersection B divided by probability of B. Okay, this is a conditional definition of probability. This is our conditional distribution of probability. Okay, and the above one is the Bayes theorem. Okay, these two are similar. These two are only for a conditional probability. So when we compare these two, we will find that probability of the event B here is summation probability of A given EI into probability of EI. This is called total law of probability. Okay, which is total law. These are just name actually. Okay, so the denominator term is total law of probability, and again the numerator term A intersection B equals A intersection B equals the probability of A intersection B equals A given EI, the probability of A given EI. We can also write B actually here if you like use a similar notation. A given B, we can write actually, let me write here A given B so that there is no confusion. A given B and probability of B. Again, this is the multiplicative rule. With that, we have already discussed. So everything is like same. From the conditional distribution, we will define the Bayes theorem. Okay. So always try to like remember the Bayes definition. Sorry, the Bayes theorem is probability of EI given A. The EI under the condition that the likelihood event has occurred is A given EI, the probability of A given AI into probability of EI, and the divided by the same element, but taking the summation over for all the exhaustive events. Okay, so these are our Bayes theorem. Actually, everyone, including me, okay, I am usually confused each and every time how to define the events EI and how to define the likelihood events and the formula even as well. Okay, many times I have forgotten the formula for the Bayes theorem because AI given A or A given AI, I was confused. But with the help of this A given B, this conditional distribution, sorry, the conditional probability, I will try to remember this formula from now onward. Okay, so just a trick if you understand this trick. Okay, so these are the Bayes theorem. Now, independent event, as we have already discussed, there is one more or one last thing, that is random variable. Can anyone define a random variable? Anyone have any idea like how to define a random variable? Anyone? Suppose we have a random variable x. Okay. So it is defined as a not variable actually. The first thing that we should know that a random variable is not a variable, it is a function. Okay. It is a real valued function actually. Okay. A random variable is not a variable, it is a real valued function. And if it is a function, then it has domain as well as codomain and range. Okay. So let me write a random variable is a real valued function of a sample space which map from the element of the sample space to a real value. That means it assign the each and every value elements of a sample space a real number, a real value. So that's why it is called a like that. And not that's why it's called a random variable, but it is a real valued function which map from the sample space to a real number or real line. So that means x is a random variable which from the sample space to the real number. That means it is just a converter which convert the sample values, which assign a sample values to a numerical value. Okay, so that we can like compare or know the weight of those particular elements in the sample space. Okay, that's very simple actually. Suppose, for example, suppose here I can example to understand the uh, two dice are rolled. Okay, we already know if we roll two dice, then we have a sample space which contain 1 1, 1 2, 1 6, 2 1, and 6 6. Okay, so there is a total of 36 element in this sample space. Okay, let me define a random variable. A random variable is defined in such a manner that the sum on the dice is, okay, the sum is sorry, the sum is 7. Okay, the sum is 7. So now we have a random variable that when we roll two dice, then the sum on the two dice comes out to be 7. So the x is actually the sum. Sum is 7. Okay. So the event A that we will associate it with this random variable is, suppose like it's 6 1, 5 2, 4 3, 3 4, 25, and 16. Okay, so the number of elements is in the event A is 6. So if we told that what is the chances that when we roll two dice, then the sum comes out to be 7, then you have 36. If you want to, like, if you try to imagine, then how many times the sum 7 occurs, you are not possibly visualize those things. Okay. Since it is two dice, though it may possible you may visualize, but suppose I told take 7 dice, then 10 dice, then you are not able to recall the sample space and then these things. So we will assign this random variable, the sum is 7, to a numerical value. How? With the help of the definition of the random variable. Okay. So that means probability of A is number of elements in A upon total number of elements, which is 6 by 36, which is 1 by 6. If you recall, it is approximately 16% or 17%. Okay. So that means if we roll two dice together, then 17%, approximately 17% of the time, the sum will appear as 7. Okay, the sum 7 will appear. Okay, but what if I told you the sum is 5? For example, what if I told you the sum is 5? And in that case, 1, 4, 2, 3, 3, 2, and 4, 1. Only these 4. So the probability of the event B is obviously 4 by 36, which comes out to be 1 by 9. If you, it is approximately 11% something. Okay, less than 12%. So 11.11 something. So if I told you, suppose we roll two dice together, then what are the chances of getting 7 as a sum and what are the chances of getting 5 as a sum? Then you may solve these things and you may find out that the probability of getting the first event, that is getting 7, is greater as compared to getting 5. Okay. So from there only you are able to assign a number with the help of the definition of the random variable. Okay, and the probability even. So this is the definition of random variable that assign a elements of, sorry, that maps a sample and from sample space to a real number, that assign a real number to the all the elements of a sample. Okay, is there any doubt in this? Then you may ask. Okay. Now there is a probability distribution as well. Probability distribution, that means we need to distribute the probability. Again, the same question, rolling two dice. Okay. Probability distribution. Okay. We need to distribute the probability. How to distribute the probability? Suppose we have a probability of 1 total. Okay. We need to distribute for all the elements. The same example, 1, 1, 2, 6, 6. Okay. We have 36 elements. And sum. X is sum on the two dice. So again, the sum occurs, the value of X is either 2 or 3 or 4 or 5 or 12. Okay. These are the all possible values of X. Okay. Now, if we have 11, total 11 cases is there. So that doesn't mean that the probability of getting 2 is equal probability of getting 3 is equal probability of getting 12. This is not true actually. This is wrong. Because here we assign or we assume that those are equally probable, but these are not the case. Okay, we need to distribute the probability. That means we need to define the weight for all these sample values. Okay, the random values, that means. So this is the distribution of probability. We need to distribute the probability. Now the next is CDF. The last topic here is CDF, cumulative distribution function. In short, we will, like in abbreviation, we use CDF, cumulative distribution probability. Usually it is denoted by capital Fx, okay, and is defined as the probability that this x is less than or equal to. Okay, so this is the definition of CDF. Again, suppose probability of getting x equal to 3, not probability. Suppose CDF that x is equal to 3. So this implies probability that x is less than or equal to 0 for the same example when we roll 2 dice for the same example actually. Okay. So here if fx is equal to 3, which implies probability that x is less than or equal to 3, which implies probability that x is equal to 2 plus probability that x is equal to 3. What if I write x is equal to 7? In that case, probability that x is less than or equal to 7, and this implies probability that x equal to 0 plus, not 0, it's starting from 2, no? 2 plus probability that x is equal to 3 plus probability that x is equal to 4 plus probability that x is equal to 5 plus probability that x is equal to 6 and 7. So CDF accumulate the probability at up to this point, up to this point. Okay, up to this point. What are the probability up to this point? The whole distribution, it will sum up. So this is the CDF, your cumulative distribution function. There are some properties of the cumulative distribution function actually. Properties of the cumulative distribution function. We have 3 to 4 properties actually, mainly 3 properties. Suppose we have a CDF, suppose we have a function and we need to check whether that capital Fx, that function is a valid or proper CDF. We need to find 3 properties. The first one is like limit x tends to minus infinity. Okay, the capital Fx comes out to be 0 and the limit x tends to plus infinity, the capital Fx comes out to be 1. If this condition satisfies, then it may possible that capital Fx is a proper or valid CDF. The second condition, this is like if x1 is less than or equal to x2, this implies fx of x1 is less than or equal to fx of x2. Here we have some notation. Always try to remember or use those notation, like capital X is the random variable, okay, and small x are the random sample. That means the value associated with those random variables. Okay, like here in the above example, when we defined the random variable x is the sum on the 2 dice. Okay, but the different values for the x is 2, 3, 4, 5 to 12. So suppose x1 is 2, small x1 is 2, small x2 is 3, small x3 is 4. Similarly, small x11 is 12. Okay, so when we use the small, then we termed as like random sample, and when we use the capital, that's nothing but random variable. So these are the standard notation actually. Capital F and capital X in subscript, and then within bracket parenthesis small x1, that means the number, the random sample, not the variable. The value associated with that random variable is random sample. So this is the non-decreasing. And the third, there is one more actually. The third property of the CDF is limit. It is continuous to the right. That means the limit h tends to infinity. The CDF of fx plus h equal to f of x. So it is right continuous actually. We have left continuous and right continuous. So it uh, follow the right continuous. So if a given function follows these three property, then we say that that function is a valid cumulative distribution function. Okay. And obviously the random variable are three types. Random variables are mainly three types. The first one is discrete, continuous, and again the mixed, which is discrete, plus continuous. Okay, so these are the topics we will discuss in week up to week 2. Okay, so let's try to solve some numericals actually. Okay, so let me write some questions and then we will try to solve the solution. Okay, like we have two cards are drawn successfully. Two cards are drawn successfully from a pack without replacing the first. If the first card is spade, if the first card is spade, then what is the probability that the second card is also a spade? That the spade. Okay, so we need to find the probability that when we draw two cards from a pack without replacing, then the probability of getting the second card, sorry, then probability of getting the second card is spade when we have a condition that the first card is already spade. Okay, so I hope everyone know the distribution of cards. If there is any problem in the distribution of cards, you may ask, or we will solve the question directly then.
Sir,
Everyone know?
sir, can you explain? Hello,
Yes,
sir.
yes.
Sir.
I can explain.
Can you explain the distribution of card? एक बार फिर से explain कर दीजिए, मैं previous class में नहीं थी.
Okay, I will explain. No problem. See, very simple. Like we have a 52 cards actually. Okay, a deck of card contains 52 cards, and on the basis of like color, it has 26 and 26. Okay, so like the 26 one red and it is black. The standard card contain 26 black and 26 red, and out of those 13 and 13. 13 cards are like diamond. There are four suits. Okay, there are four suits. 13 are of them are diamond. Diamond are red in color, and there are heart. 13 are of heart, and in a similar manner, 13 cards are like spade, and the rest 13 is club. Okay, so there are actually some designs are there. Okay, so those are designs are like diamond, heart, spade. Okay, and their last one is club. Okay, so these are the four different suits, and every card has like 2, 3 up to 10, and there is four alphabetical cards: Jack, Queen, King, Ace. Okay, so these are the 13 cards, and all the 13 cards have like diamond, okay, and heart, and spade, and clubs. So we have a total of 52 cards. Okay, now in our question, actually there are four. Every card has four. Sorry, like every number. Suppose two, there are four cards in our like deck of cards, and each card have different. Each four cards have different suits. The one is diamond, the another one is heart, and the rest two are spades and clubs. Out of them, two are red and two are black. Okay, so these are symmetrically defined. Now, I hope you will understand. Uh, we will solve now questions. Okay, two cards are drawn successfully from a pack without replacing the first. If the first card is spade, we have 13 spades actually. If you can see, you will find we have 13 spade cards. So the question is, if the first card is spade, then what is the probability that the second card is also a spade? This is the question. Now it's a very simple question actually, because we already know the distribution of a card. We replace the first card. So out of 52 cards, we replace one spade card. Okay. So when we replace one spade card, then we have a total of 51 cards, and in that 51 cards we have 12 spade cards. 12 spade card. Okay. Now our question is, what is the probability of getting a spade card? Given the first card is spade. The first drawn card is. So in our favorable condition, there are 12 cards and a total of 51 cards. One lack, one card is lack because we use without replacement. So it's 12 upon 51. So the required probability is 12 upon 51. We will divide by 3. That means 4 upon, not, not 13, it comes out to be 17. So this is the required answer. Is it okay? Or is it okay up to this point? Anyone?
Yes, sir.
Yes, sir.
Okay, thank you. So this is the simple question. Now the second question is, 4 of the 7 balls in a box have odd numbers on them. 4 of these 7 balls in a box have odd numbers on them. What is the probability that what is the probability that all 3 balls picked at random, all 3 balls picked at random, one after the other, without replacement. Always try to remember the question as with replacement or without replacement. Have odd numbers. Can anyone tell the result? Okay, the question is, we have 7 balls. Out of those 7 balls, 4 have odd numbers. Okay. So suppose we have a box and we have 7 balls. And suppose 3, 4, 5, 6, 7. So obviously we have 4 odd number balls and 3 even number balls. Now the question is, what is the probability that all 3 balls picked at random, one after the other, without replacement, have odd numbers? So that means we need to pick 4 balls. Okay, we need to not 4 balls, 3 balls. No? We need to pick 3 balls actually. All 3 balls. We need to pick 3 balls. So first, we need to the required probability is what? We have in favor odd number of balls. So 1, 2, 3, 4. We have in favor 4 balls. Okay. And total number of balls is 7. Now in second step, we will not replace those balls in the box again. Then in the next successive draw, we have 3 favorable outcomes, and out of those, we have a total of 6 outcomes. The second ball, which must be an odd, is 3 by 6. Now, the third ball has odd numbers, have favorable number of counts, 2. Now we have a 2 odd balls in our box, and a total number of boxes there is 5. Okay. So obviously it's 4 by 7 into 3 by 6 into 2 by 5. Simple. Now we need to solve this. Comes out to be it's 4 divided by 35. So there is a very less chance, like 1 by 9, 11%, approximately 11% chances that when we draw 3 balls one after the other without replacement from a box containing 4 odd and 3 even balls, then all the 3 balls are odd, has 11% chances. Okay, so this is how we use our the concept of random variable, the concept of probability. Okay, so there is a very less chance. You can create your own question for the same problem. Okay, for the same sample space. Suppose we draw 2 balls one after the other. Okay, with replacement. What if I draw 2 balls with replacement, and the 2 balls have, and we are like find even number of balls. For example, I'm just creating a question actually. Okay, so the probability 2 balls one after the other, 2 balls are drawn one after the other with replacement. Okay, and even all those 2 balls are even, not events, even. Then can anyone tell what is the
Sir.
probability? Yes.
Sir, may I tell?
Yes. Yeah. Sure.
Sir, 3 by 6 into 3 by 3 by 7 into 3 by 7, because probability will not change, because the ball which we are taking out, we are replacing that ball, so the sample space will not change.
And what if we do not replace the ball?
Sir, then 3 by 7 into 2 by 6.
2 by 6 comes out to be 1 by 7. Okay. So one comes out to be 1/7, and this one comes out to be 9/7 times 1/7. Okay, so that means the first times when we replace the drawn ball, then in that situation the probability of getting the even ball is higher. How much times? 9/7 times higher as compared to when we not replace the ball in the same box. These we will use in our higher concept as well. Okay, here you can see, like when we draw two balls one after the other, when we perform with replacement experiment and without replacement experiment, the probability is higher in with replacement with a factor of 9/7. You can see here. In sampling theory, in case you will know or in future that we will discuss about the sampling with replacement and sampling without replacement concept. Okay, so here again with replacement and without replacement. Okay, you may also create more problems with the help of the same question. So up to this point, is it okay? Na?
Yes, sir.
Okay. Now again, we have one more question. So the question is like two urns contain respectively. Try to solve this question. Okay, two urns contains respectively two white and one black balls, two white and one black balls, and one white and five black balls. One ball is transferred. Now the question is one ball is transferred from the first to the second urn. From the first to the second urn. And then, sorry, and then a ball is drawn. And then a ball is drawn from the second urn. What is the probability that the ball drawn is white? That the ball drawn is white. Sorry. Just try to solve this question. Just try to solve this question. Okay. So I'm solving, and you too, please try to solve. Here you can see we have two urns actually. Okay. So the first urn, suppose U1, and the second urn is U2. The first urn contains two white and one black ball. Two white and one black ball, and the second one white and five black balls. Now, one ball is transferred. One ball is transferred from the first to the second urn. Okay. So obviously, if we select one ball from first urn, it may possible that the ball is either white or black. So we have two conditions actually. the condition 1, suppose it's C1, white ball is transferred. White ball is transferred. That means if we, in first case, transfer one white ball from urn 1 to urn 2, then the urn 2, then the second urn contain 2 white ball and 5 black ball. Okay. And the probability of getting a white ball in urn 1 is 2 by total number of ball 3. Okay. So these are all the pictures. And the second case, black ball is transferred. Okay. Then the second case, black ball is transferred. Then the urn 2 contain 1 white ball and 6 black ball. These are the two conditions. Okay. So actually we modified our sample space kind of. Okay. Now the question is, one ball is transferred from the first to the second urn, and then a ball is drawn from the second urn. What is the probability that the ball drawn is white? Okay. So the ball drawn is white. The probability that white ball when C1 occurs, when the condition C1, the case C1 occurs, then the probability of getting white ball is total number of white ball is 2 and total number of ball is 7. But this is the condition multiplied by what is the probability of drawing a white ball from first urn to the second urn. Total number of ball is 2, white ball is 2 and total number of balls in the urn 1 is 2 plus 1, which comes out to be 3. So it comes out to be 4 upon 21. In the same case, the probability of getting white ball when the black ball is transferred from urn 1 to urn 2. So when black ball is transferred, then the probability of getting white ball is 1 divided by 7 multiplied by, there is only one black ball in urn 1. So obviously it's 1 by 3 comes out to be 1 by 21. So the probability of getting white ball is 4 by 21 plus 1 by 21 comes out to be 5 by 21. Is it okay up to this point? Is there any doubt in this question? Anyone? Okay. We will solve the next question. Now we have a question based on total law of probability. Okay. So there are two boxes. There are two boxes. Box 1 contains 3 silver spoon and 3 copper spoon. 3 silver and 3 copper spoons. And box 2nd contains 5 copper and 3 silver spoon. 5 copper and 3 silver spoon. Assume the box 1 is likely to be chosen with a probability of 2 by 3. Now we have a probability of choosing the two different boxes as. Okay. So assume that box 1 is likely to be chosen. Box 1 is likely to be chosen with probability with probability of 2 by 3 and box 2 with probability 1 by 3. Okay. So the probability of choosing box 1 is 2 by 3 and the probability of choosing box 1 is 1 by 3. To this point, is it okay? Now a spoon is chosen at random from a box. Now a spoon is chosen at random from a box that has been randomly selected. That has been randomly selected. What is the probability that it is a silver spoon? What is the probability that it is a silver spoon? Okay, so it's a simple question. We have two boxes. Let me write here. So we have two boxes actually. Okay, the box 1 and the box 2. Box 1 contains 3 silver and 3 copper balls. So we have 3 silver balls and 3 copper balls. S for silver, C for copper. And box 2 contains 3 silver box and 5 copper box. Okay. Now the question is the probability of choosing box 1. So probability of choosing B1 is 2 by 3. Probability of choosing box 2 is 1 by 3. Okay. Now we randomly select a box and then from that box we randomly select a spoon and then we need to find the probability that the selected spoon is a silver spoon. Well, that it is a silver spoon. Okay. So let's start. We the probability of getting silver spoon when we select box 1 is probability of silver. Sorry, let me write here in that manner. Actually, we need to write the total of probability. Na? So probability of getting a silver spoon. So probability of getting a silver spoon, we have two possible outcomes when we select the box 1 or when we select a box 2. When we select a box 1, the probability of getting silver given box 1. When we select the box 2, the probability of getting silver spoon given box 2. So this is the required probability. Now we will solve the numerical value. Probability of getting B1 is 2 by 3. Probability of getting silver when we choose box 1 is total number of silver box is silver spoon is 3 and total number of spoon in the box is 3 plus 3 which equals 6. Plus probability of getting box 2 is 1 by 3 multiplied by probability of getting a silver spoon is 3 and the total number of spoons in the box 2 is 8. So it comes out to be 1 by 3 plus 1 by 8. So not approximately, it comes out to be exactly, it's 11 by 24. You may write. So probability of getting silver spoon is 11 by 24. Is it okay up to this point? Or is there any doubt? Anyone?
Yes, sir.
Okay.
Yes, sir.
Now, okay, thank you. Now we will solve some question based on the Bayes theorem directly. Okay. So the question is, let me write here. The chance that a certain disease, chance that certain disease is diagnosed correctly is 60%. The chance that the patient will die, the chance that means the probability that the patient will die under the treatment after correct diagnosis. After correct diagnosis is 40%. Okay. And the chance of death and chance of death by wrong diagnosis is 70%. Okay. Now, a patient who had the disease died. A patient who had the disease died. What is the probability that his or her disease was diagnosed correctly? Disease was diagnosed correct. Okay. So this is the question. I really wanted to know that how to define the exhaustive events E1, E2, E3, and the likelihood event, that is AI, that we have defined in the Bayes theorem. Can anyone help me out with this? Like here we have the question. The chance that a certain disease is diagnosed correctly is 60%. That the 60% times we correctly diagnose that there is a disease. And the chance that the patient will die under the treatment after the correct diagnosis is 40%. When we correctly diagnose the disease, there is a 40% chances that the patient will die. And if we are unable to correctly diagnose the disease, then in that case, 70% of the time the patient will die during the treatment. Now, a patient who has died, then we need to find the probability that the disease was diagnosed correctly. Can anyone?
Sir, the
Okay.
likelihood event will be
Yes. What is the likelihood
the
event?
likelihood the disease that was diagnosed correctly.
The likelihood event. Okay, let me write with this color for you. The likelihood event, according to you, diagnosed correctly, no? Okay. Then what are those exhaustive events, that is E1 and E2 kind, that we have defined in the theorem?
So sorry, sir, the patient who had disease died. That would be the
Okay. So that would be the likelihood event. Now this time you are right, actually. Okay. So the likelihood event, let me write it with the D letter for the died. So the patient will die. Okay. The patient will die. This is the likelihood because the death occurs in both the scenario, whether the diagnosis is correct or it is wrong. In both the scenario, there will be death. Okay. So this is the likelihood event. Okay. That associated with all the exhaustive events. Now, what are those exhaustive events actually? So the first one is E, is the disease is diagnosed correctly. And the next one, what will it be?
Disease is not diagnosed correctly.
Diagnosed wrongly. Okay, incorrectly or wrong. Okay, so we have now the setup for the Bayes theorem. Now we have exhaustive events, that is E1 and E2, which is diagnosed correctly or diagnosed wrong. And we have a likelihood event associated with those, that E1 and E2, that is the patient will die. And if you read the question, you will find all the prior information related to these events that we have defined here. What? The probability of E1. The first one is probability of E1. That is the diagnosed correctly. So what is the probability that the chance that the certain disease are diagnosed correctly is 60%. So we have probability of E1 is 60%. Now the probability of E2, what will it be? Can anyone? It is not given here actually. 60% it will diagnose correctly. So obviously 1 minus 60%, that is
40%.
yes, 40%. So 40% of the time they are unable to diagnose the disease correctly. So the probability of E2 is 40%. Now the death. Death occurs under E1 and E2 both. So probability that death occur when E1, when diagnosed correctly. When diagnosed correctly, that there is a 40% chances, 40% chances that the death will happen still the diagnosed the correctly. The disease is diagnosed correctly. So probability that D given E1 is again 0.40. Now probability that that will happen when diagnosed incorrectly. So it is already given 70%. Okay. So we have all the setup for the Bayes theorem. What we need to find? We need to find a patient who had the disease died. What is the probability that diagnosed correctly? Diagnosed correctly means E1. So we need to find, let me write it here, the formula. We need to find the probability that diagnosed correctly. Diagnosed correctly means probability of E1, but the death has happened. Okay? See here, a patient has died. We need to find the probability that the patient was diagnosed correctly. That means D. We need to find probability of E1 given D. So let's write the Bayes theorem. Now the Bayes theorem is probability that E1 given D equals try to solve probability
Sir,
of
6 by
E1
13.
6 by 13. Okay, this is the right answer actually, but let me write. Okay, so probability of E1 given D is D given E1 into probability of E1 divided by probability of D given E1 into probability of E1 plus probability of D given E2 into probability of E2. So obviously D given E1 is what? 0.4 multiplied by probability of E1 is 0.6 and divided by 0.4 into 0.6 plus probability of D given E2 is 0.7 into probability of E2 is 0.4. So 0.24 divided by 0.24 plus 0.28. So obviously after solving, anyone can solve this now, comes out to be 6 by 13. So approximately you can see 50% chances that the patient had died and the disease was diagnosed correctly. Okay, so I think, like, I hope you understand the question and the solution as well. Is it okay?
Yes, sir.
Yes, sir.
Okay. Thank you. Now the next question. The next question is, let x be a discrete random variable. We have let x be a discrete random variable, is abbreviated as RV, okay, with the probability mass function PMF. Actually, it is nothing, just a probability distribution, okay, for the discrete random variable. As so, we are given x value and we are given probability value, okay. So we have -2, -1, 0, 1, and 2. So we have 5 different possible values for the random variable x, which is -2, -1, 0, 1, and 2. And the associated probability is like 1 by 9, 2 by 9, 3 by 9, it's 2 by 9, and again the 1 by 9. Okay. We need to find the probability that modulus of x is greater than or equal to 1. Can anyone solve this? Try to solve and let me know the answer. I will solve here as well. So we can write probability of x is greater than or equal to 1 equal to probability that -1 x1 equal to 0. So this implies probability that x equal to -1 plus probability that x equal to 0 plus probability that x equal to 1. So probability that x equal to -1 is 2 by 9 plus 3 by 9 plus 2 by 9. Obviously, it's a very simple question actually. It's 7 by 9. So 80%, more than 80% chances that the probability will lie within the -1 to +1 range. Okay, simple question actually. Now there is one more question actually. There are 2 or 3 questions that I've written. Let me write a trick question. Let me see if people may solve this or not. The question is, we have 2 events A and B. Okay, 2 events A and B satisfy probability of A equal to 0.7, probability of B equal to 0.6, probability of A given B equal to 0.5. Okay, we have 2 events A and B, and the associated probability with these events A is 0.7, probability of B is 0.6, and probability of A given B is 0.5. We need to calculate the probability of A complement given B complement. We need to find this. So can anyone try to find this? Just try. It's a very
Sir,
like kind of, yes, yeah. Try. Let me write even here as well. Since we are given probability of A given B, and we know the probability of A given B, yes, is it
7 upon 4.
7 upon 4. Okay. Just try to see this. It's 1.75 and the probability lie within 0 to 1.
Oh, sorry. So,
No problem. Just try. Okay. It's a kind of not exactly tricky question actually. We need one theorem that is like one law that is De Morgan's law here actually. Okay. So probability of A given B is probability of A intersection B. Let me erase this. So A intersection B upon probability of B. This is the conditional definition of probability. Now from here, the probability of A intersection B comes out to be probability of A given B multiplied by probability of B. So probability of A given B is 0.5, probability of B is 0.6. So probability of A intersection B comes out to be 0.30. The first one is we have calculated A intersection B. We need to find probability of A complement given B complement. Okay. So again, the formula is like probability of A complement intersection B complement divided by probability of B complement. Now we have one theorem that is De Morgan's law. Okay, sorry, not theorem, it's a law actually. We have a De Morgan's law. And what it is like we can write A complement intersection B complement as A union B whole complement. A union B whole complement. Okay. So that means we can write this expression, this equation star. Let me write it equation star. This equation star as probability of A union B complement divided by probability of B complement. So our next step is to find the numerator and the denominator. Let me write it double star, for example. Okay. So we need to first find probability of A union B complement and probability of B complement. So probability of A union B complement. A union B complement is nothing but 1 minus probability of A union B. Simple. And 1 minus probability of A union B is what? Probability of A additive theorem plus probability of B minus probability of A intersection B. Simple. Now 1 minus probability of A is what? Probability of A is 0.7, probability of B is 0.6, and probability of C is 0.3. Not C, it's A intersection B. So 0.7 plus 0.6 minus 0.3. And you will find 1 minus 1. So our the intersection probability A union B complement comes out to be 0. A union B comes out to be 0. So the numerator term in double star comes out to be 0. So this implies probability of A complement given B complement comes out to be 0 upon probability of B complement, which obviously A complement given B complement comes out to be 0. Is it understood up to this point?
yeah.
Okay. So there is some set properties actually. Okay. Like every property which holds in set theory should also holds in probability theory. Okay. So yes, there is one more question. Let me write one more question. A random variable x X has the following probability mass function as the following probability mass function. Like we have X and we have probability that X equal to X. And the values like 0, 1, 2, 3, 4, and 5 with the corresponding probability is 0, 2k, 3k, 2k square, 4k, 9k square plus 5. Sorry, it's not 5. It's 9k square plus k. Okay. So this is the PMF, the distribution of probability under the discrete random variable. Okay. So first thing is, actually the question is, let me write the full question first. Find probability that X is less than 3. Okay, this is the question. We are given the distribution of probability is like this. We need to find the probability that the random variable X will possess the value less than or equal, not equal to, less than 3. Okay. So first of all, we need to find the K value. Okay.
Sir,
Do you
will
know
we
how?
give-
Yes, yes.
Sir, we will add all the probabilities and it will sum will be 1.
Yes, exactly. Because we know that the properties of the PMF, like the summation over the range X, comes out to be 1. So we have 0 plus 2k plus 3k plus 2k square plus 4k plus 9k square plus k comes out to be 1. From here, 2, 3, 5, 4, 9, 10. It comes out to be 10k, and 9 plus 2 plus 11k square comes out to be 1. It's a simple quadratic equation now. 11k square plus 10k minus 1 comes out to be 0. 11k square plus 11k minus k minus 1 comes out to be 0. Simple now. If you have any doubt, you may directly ask. We will take 11k as common, k plus 1 minus 1 we will take as a common, then it will again k plus 1 comes out to be 0. Now we will take k plus 1 as common, then it's 11k minus 1 equal to 0. So we have either k plus 1 equal to 0 or 11k minus 1 equal to 0. So from here k equal to minus 1 or k equal to 1 by 11. So again, without any doubt, we know that according to the axiomatic definition of probability, the probability will neither go to negative value. So this will not hold the case. So the value of k is 1 by 11. Okay. Now we will come to our question that we need to find the probability that x is less than 3. Okay. So probability that x is less than 3 equals probability that x equal to 0 plus probability that x equal to 1 plus probability that x equal to 2. Or should we write the probability that x is equal to 3? So no,
No, sir.
because x is, yes, x is less than 3, not equal to. It's strictly decreasing. So we need to find x equal to 0. So probability that x is equal to 0 is 0. So we will write here 0 plus x equal to 1 is what? 2k. X is equal to 1 is 2k plus x is equal to 3. Sorry, x is equal to 2 is 3k. Okay. So this is the probability. So it comes out to be 5k. We put the value of k. So we will get probability that x is less than 3 comes out to be 5 upon 11, which is approximately 45% or 46%. Okay. So 45% of the time. So this is actually the case. Okay. Is there any doubt?
Yes.
Okay. So let me write one more question, and this one is also belongs to the Bayes theorem. Okay. So I hope you will try to solve this. We have three machines. Okay. Three machines. Let's name the machine M1, M2, M3. Manufactures 30%, 45%, and 25% of the total products. The defect rates are 2%, 3%, and 4% respectively. If a product selected at random, if a product selected at random, a product selected at random is found to be defective, it's found to be defective, then find the probability that it was manufactured by machine 2. It was manufactured by second machine, that is machine 2. Simple question. We have three machines. Machine 1 manufacture 30% of the product. Machine 2 manufacture 45% of the product, and machine 3 the remaining 25%. Okay. And since these three machines may produce some defective items, and those defective rates are 2%, 3%, and 4%, we need to find the probability that a randomly selected product is found to be defective, then it is belongs to or manufactured from machine 2. Okay. The question is okay. So let's try to solve the question. So let's define the element D, defective elements. And M1, M2, M3 are the machines. So probability that M1. So see, if you can see, you will find the three machines have not produced the similar amount of products. Okay. So the machine 1, M1, that is the machine 1 produced 30%. So the probability that 30% of the product will manufactured from machine 1. Again, machine 2 is the most one, that is 45%, and machine 3 have produced 25% of the product, 0.25. Now the rates, the defects, probability that the product is defective given machine 1 is 2%, so 0.02 actually. Similarly, the defective given machine 2, it comes out to be 0.03%, and the rest is defective from machine 3 comes out to be 0.25, no, 4%, 0.04%. Okay. So we need to find that what we need to calculate. The product is defective. This one is sure. This one is sure. It is found that the product is defective. Find that it is from machine 2. So we need to find what? We need to find the machine is M2 given the product is defective. So to formalize probability the defect given machine 2, probability that machine 2 divided by again probability that defective given machine 1 into probability that machine 1 plus probability D given machine 2 into probability that machine 2 plus defective given machine 3 into probability that machine 3. So these are the cases. Okay. Now the sample, we need to put the values and solve. So D given M2 is what? 0.03 multiplied by M2 is what? 45. So 0.45. D given M1 is 0.02 multiplied by 0.30 plus 0.03 multiplied by 0.45 plus 0.04 multiplied by 0.25. Just simple cal. Yes?
Sir, 27 by 59.
27 by 59. Okay, 27 by 59. So obviously it may come approximately. I don't know this answer is right or not. My answer will be like 4, 5, 7, 9, which is approximately equal actually. If
Yes,
you will solve
yes, sir,
by a
this is
calculator.
same.
Yes. So obviously that means what? You need to like interpret the result as well. Okay. In future, if you are like wanted to understand the probability, you need to interpret every result. So you can see our machine 2 will produce 45 or 46% of the defective items. Okay. So machine 2 produce the more defective items as compared to the other two. It is clear. But here if you see, you will find out a machine. Wait, let me do this. Okay. Here you can see machine 3 will produce 4% defective item. Okay, which is the highest in the all three. But in overall, if you see, you will find out since machine 3 produce only 25% of the product. Okay, and machine 2, which produces around 45% of the product, is producing around 46% of the defective product. Okay, so overall defective proportion is around 46%. So obviously, if you have to replace one machine, then that will be machine 2. Is it okay up to this point? Is it okay?
Yes, sir.
Okay, thank you. Okay, I think we have all the questions. If you have any question, you may ask actually. Okay. I have covered all the questions related to the total law probability, the Bayesian theorem and all. If you have anything you want to ask or want to share anything, you are welcome. Okay.
Sir, can we practice the transfer ball, another type of numeric, this related to this numerical?
Okay. So you want to write me a question on those topic actually. Hello.
Yes, sir.
So means you want I like there I should solve one example on those topic.
Yes, sir. Like we solved one question, so can we solve another question?
Okay. Okay. I will try, but I don't have the question actually. I've written all the question so that I can solve it here. But we will discuss actually. We will discuss here. I don't know. I'm going to solve the question right. So let's create a question together. What kind of question you want here? If you help me out with this.
So like there were two ones and it has different types of balls, red and black balls, red and black balls. And
Okay. Yes, just create any question. Let's see we will able to solve those or not. If not, then let's we will solve later. Otherwise, we will solve here only. Suppose we have box one. Okay. We have box one containing 6 red ball and blue. Suppose 4 black ball. Make it simple so that the total number ball is 10. Okay. And we have another box, which is box two. It contains how many red and how many black balls or blue balls as there?
so five, five.
5, 5. Okay. No problem. Okay. So we have this question. Now, the similar kind of question that we have solved in the above slide, that we place one ball from B1 to B2. Okay. One ball, not balls, ball. Okay. One ball from B1 to B2. Okay. And no, I'm not going to complicate the problem. If I'm complicated the problem, I'm not able to solve the problem. Okay. So first, stop here. Okay. So when we transfer one ball from box one, let me write it earn one, not P1, so that is better for me. You too. So earn one and earn two. Okay. Yeah. So what is the probability that the transferred ball is red? It may one question. So the question will be like find the probability that, okay, the question will be like this. Okay, I'm not going to write all the question. I'm going to say here, like when we transfer one ball from earn one to earn two, then and then draw one ball randomly from earn two, then what is the probability that the randomly drawn ball is a blue ball? Okay, the randomly drawn ball is blue ball. Hello. Sorry. Okay, so the probability that the blue ball is, how can you solve this? Can you find out the result? Then we will like more like we will frame more question. But the first question is we will randomly select one ball from the earn two, find the probability that it will be the blue ball. Okay.
Yes, sir.
So, so the probability of the blue ball is probability of, okay. So again, we have two questions actually. I was confused to frame a question instantly. So there is case one. The case one is transfer red ball, and case two is transfer blue ball. So if transfer red ball, then in that case, red ball is equal to 6 and blue ball equal to 5. And what if transferring blue ball, red ball equal to 5, blue ball equal to 6. And also probability that first condition, uh, in C1, transfer red ball, then probability of blue ball is, we write like this, blue
5
ball
by
given C1. What is 5 by?
5 by 11.
Is it okay? No. There is one thing is missing
By
here,
11
and the
into
into the red one. 6 by 10. Exactly. 6 by 10. So it comes out to be 3 by 11. You solve, you will find out 3 by 11. Okay. Now again the probability of blue ball given C2, it comes out to be, so blue ball given C2, that blue ball is transferred. So if the blue ball is transferred, then it's 6 by 11 multiplied by blue ball is transferred, so 4 by 10. Okay. So it's what it is, it's 24, or it's 12 actually, 12 by 50. Okay. So this is the question that I can directly frame. Now it's the simplest one that we can frame. The second one, what we can frame here, can anyone help me? The second question that we can frame here with the help of the scenario that we have discussed.
Sir,
We,
find the
yes,
probability ball.
sorry, finally,
Find the probability of a red ball.
okay, the similar kind of actually, yes, yes. So probability of red ball. Under C1, again, the condition is same, the above condition is same. Okay. Under C1, probability of red ball. So the probability of red ball is what? 6 by 11. It's 6 by 11 into, since from here, 6 by 11 red ball, that is 6 by 10. Comes out to be 18 upon 55. Similarly, probability of red under the condition or case C2. So the case C2 is the case C2 is 5 by 11 multiplied by 4 by 10, comes out to be 2 by 55. Okay. I can frame some more question, but I'm not sure that I can solve that question directly.
Only
Yes.
one question enough.
Okay. So let's, like, would you like to frame one more question?
Sir, based on the same thing or other?
Let's try one more question. I'm not sure I will solve, but I will try actually. What if I transfer two balls? Then the question will be much complicated actually. Let me try. Okay. It's actually recorded. So urn 1 contain 6 red and 4 blue balls, and urn 2 contain 5 red and 5 black blue balls. Okay. I am going to transfer two balls now. So the cases will be like more. Okay. So the case 1, the 2 red ball will be transferred. The case 2, 2 blue ball will be transferred. And the case 3, not 2, it's 1. It's 1 red and 1 blue ball will be transferred. Okay. Is it okay up to this point?
Yes, sir.
Okay. So now our like modified sample space, how it looks actually. Under case 1 scenario, let me, under case 1 scenario, if 2 red balls, then 7 red balls and 5 blue balls. It belongs to C1. Under C2, 2 blue balls. So 2 blue balls, that means 5 red balls and 5, sorry, not 5, 7 blue balls actually. 7 blue balls. This is under C2 condition. And under C3, it's again 6 red and 6 blue. C3. Na? Now, our question is again the same, either red or blue. So probability that red ball. So probability, let me write it like under all three cases. Red under C1. probability of getting red ball under C1 is what? It's 7 by 12. 7 by 12 multiplied by 6 by 10 comes out to be 7 by 20. Red given C2 comes out to be 5 by 12 into 6 by no blue ball na? Now when you transfer to blue ball it's 4 by no? It's 4 by 10 now. I will explain. Let me first solve. Try to understand by yourself as well. Okay, let me explain continuously. Here the red ball under C1 condition is 7 and total number of ball is 12. So 7 by 10 multiplied by, since under C1 two red balls transfer. So the probability of selecting two random red balls is 6 by 4. Actually there is one, I think one concept is missing that I'm unable to recall, because selecting two red balls has different scenarios as well. Like first we select one ball. Okay. See, this is how I'm stucking here. From the earn one, selecting one ball, red ball is 6 by 10. The another one is 5 by 9. Actually. Okay. So here writing 6 by 10 is okay, but also we need to write 5 by 9 here. I'm not sure I'm doing it right or not, but looks correct. 5 by 9. So this is the probability. Are you able to understand the concept? This is the probability, because selecting one ball, transferring one red ball, then again selecting the one red ball and transferring is 6 by 10 into 5 by 9. Now the total number of red balls is 7 and total number of blue ball is still 5. So the total number of ball is 12. So 7 by 12 is our favorable condition under C1, and the probability of transferring two ball from earn 1 to earn 2, which are red, is 6 by 10 into 5 by 9, which comes out to be, after you can solve this actually, 7 by 12 into 6 by 5 into 5 by 9. Okay, this is our required probability under C1. What is under C2? Under C2 is 5 by 12 into 4 by 10 into 3 by 9. Okay. And under C3, are you able to understand?
Yes, sir.
Yes. If you have doubt, you may ask. Okay. So this is the case. And under, in which one red and one blue. Okay. So again, you need to find the probability of selecting one red and one blue ball. Okay. I'm not considering the ordering. Okay. I'm not consider the ordering. So in that scenario, it will like 6, 6. No? So red ball is 6 by 12 multiplied by, it's 4 by 10 into 6 by 9, or 6 by 10 into 4 by 9. So this is the third case. So the probability of selecting the red ball comes out to be probability of getting the red ball under C1 plus probability of getting the red ball under C2 plus probability of getting the red ball under C3. So this is the required probability actually. You may solve with the help of the calculator, okay, and you may find all the answers. And yes, if the probability of getting a red ball is comes out to be more than one, then that means we frame the wrong question. But I thought we are selecting, like we are framing the right question actually, because the numerator term is like what? Hey, the denominator term is 12 into 10 into 9. The numerator term is 7 into 6 into 5 plus 5 into 4 into 3 plus 6 into 4 into 6. If you can solve, you will find 210 plus 60 plus 24 into 6 comes out to be 144. Yes. And it's again, so obviously it comes out to be less than 1. Approximately less than half actually it comes out to be if you are going to solve this. So is it okay up to this point?
Yes, sir.
Okay. So anyone have any more question, or you have any more question? Anyone?
Yes, sir.
Okay, thank you. Okay, then I think we should conclude our session here. Okay. So let me first stop the recording and thank you everyone. Okay. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.